at each kind of possible point, all of my probabilities are going to have to add up to 1 because something has to happen. And we're kind of thinking about, I like the diagram version of it where I'm thinking about moving between states, whether that's, you know, I'm going to go on DoorDash and pretend I've only got 3 options for dinner tonight. Like, what's the probability that I'm going to choose to order from Thai Canteen versus I'm going to choose to order my DoorDash from Guad's? And then tomorrow night, based on how I was feeling about my dinner last night, if I'm going to DoorDash again, maybe I'm going to choose a different restaurant. Maybe I'm not, right? But we're really going to operate in Markov chains using some of our matrix tools. I think TC for Thai Canteen, and we need another restaurant. So I'm going to go G for Guad's. And because I love Thai Canteen, I'm going to say that this is not at all realistic. Again, I'm just making some stuff up here. So if I ate at Thai Canteen last night, I really love Thai Canteen. So there's still like a 60% chance that I would order it again. So that 60% chance it's coming out of Thai Canteen because that was my state last night. And then it's going back into Thai Canteen, sort of representing that's what I'm going to order again. Well, super simplified system. And we're saying I'm only ever going to eat at Thai Canteen and Guad's. So if there was a 60% chance that I was going to eat again at Thai Canteen, that means that there's a 40% chance that I was going to eat at Guad's. Now, I do like Guad's, but I like Thai Canteen more. So if I ate at Guad's last night, let's say that there's a 30% chance that I'm going to eat at Guad's again. And that means if there's a 30% chance I was going to eat at Guad's, what does my percent need to be switching from Guad's to Thai Canteen? So, I think that to decide where we're going to order tonight, we're going to flip a coin. So if I'm going to flip a coin, there's a 50-50 chance that I'm starting at Thai Canteen tonight or that I'm starting at Guad's tonight. So if I start with a 50-50 chance, the question is, 1 night from now, 2 nights from now, 10 nights from now, where will I be eating? And because I just made these numbers up, it might get ugly, but we'll handle it. So if I wanted to do this and just like write everything out, really we're thinking about I can think about this using decision trees. So initially, there was a 50-50 chance of me choosing Thai Canteen or Guad's. But if I chose Thai Canteen tonight, then tomorrow night, I could also end up eating at Thai Canteen or Guad's. If I start at Thai Canteen, there's a 60% chance that I'm going to eat at Thai Canteen again, which means there's a 40% chance I was going to eat at Guad's the next night. If I started at Guad's, there was a 30% chance that I was going to eat at Guad's again, and a 70% chance that I was going to switch to Thai Canteen. So this is my initial state. And this is after 1 step. And if we kept going with these branches, we'd find the 2-step, the 3-step, the 4-step. If I want to know what's the probability that after that on the second night, I'm gonna eat at Thai Canteen, there's two ways that that can happen. Either I started off at Thai Canteen and then I stayed with Thai Canteen, or I started off at Guad's and then I switched to Thai Canteen. So this would represent my total probability of ending up a Thai Canteen customer after that one step. Similarly, if I wanted to know total probability for Guad's, there was a 50% chance that I started at Guad's. Sorry, there's a 50% chance that I started at Thai Canteen and switched to Guad's. There's a 50% chance that I started at Guad's, and then a 30% chance that I stayed at Guad's. And so that's my total probability for Guad's. Now, doing this math over and over again, we have much better tools than just writing out decision trees now that we've got all of our matrix tricks. So totally, I'm sure there's a reason for it. I don't know the reason for it. This is just one of those, the mathematicians decided to set it up this way. So if I think about the transition matrix, we have a choice of what goes in my columns and what goes in the rows. But let's just say some old dead white guys made a choice for us, and the choice they made was that this is the from side and this is the to side. So if I'm going from Thai Canteen to Thai Canteen, that probability was 60%. If I'm going from Thai Canteen to Guad's, that was 40%. From Guad's to Thai Canteen was 70%, and from Guad's to Guad's was 30%. So the thing to know, because of the way we're organizing it here, is that each row adds to 1. The other thing about organizing it this way, it means that we end up having to use a row vector times our transition matrix to get back another row vector. So if I were setting this up for like our first iteration here, we started off with 50-50. We had our transition matrix 0.6, 0.4, 0.7, 0.3. And I would do rows times columns to get my new row vector. So 0.5 times 0.6. Plus 0.5 times 0.7 is the first entry. So that first entry is my Thai Canteen. And my second entry would be 0.5 rows times columns times 0.4 plus 0.5 times 0.3. So that's my Guad's entry. Well, what happens if I do this over and over again? Every night I'm making the same choice. So I started at an initial state, but every night I'm going to follow this transition matrix to figure out what my probability of eating somewhere is. I'm going to flip the page unless someone needs me to write this. I'm going to try to remember my matrix 0.4. So our transition matrix is, I lied, I tried to remember it. I just 0.6, 0.7, 0.4, 0.3. Cool. So if I started at 0.5, 0.5, and I wanted to know after 2 nights, if I think about this, what's happening is we're doing our matrix of probabilities, or writing it as a vector, times our transition. And I'm going to write this, I'm going to write this as, if I use my starting probability distribution, I'm going to get my next probability distribution. And then if I take that and I multiply by t again, I'm going to get my second. But this came from taking that initial distribution times t, which means that sort of our shortcut here is to just take my initial condition times the square of the matrix to get the second state. So there are a bunch of problems in the homework where really we just have to square the matrix to get to that second transition state. Or if I needed the third transition state, I'm going to cube the matrix. Okay, I'm going to pause for a second. This is not something you talked about in lecture. I don't know if you're going to talk about this in lecture. I'm blending things that we were just doing with eigenvalues and eigenvectors for a second. So, taking it back to the eigenvector eigenvalue stuff, because I don't think he's going to have time to do this, but it's sort of cool. What it means to be an eigenvalue eigenvector pair is that if I take my matrix and I multiply by the eigenvector, I get the eigenvalue times the eigenvector back. So if I imagine doing this repeatedly, so grabbing this as my new matrix, then this tells me I've got lambda times V1A, which means that's going to pop out another lambda for me. So in particular, if I have an eigenvalue eigenvector pair, doing a to the n times that eigenvector is equivalent to just multiplying lambda times the n times the eigenvector. What that actually allows us to do is we can form a matrix of our eigenvalues and form a matrix of our eigenvectors. And it turns out it makes it really, really quick to figure out what a matrix to the nth power is. And if we had more time with Markov chains, we would build that connection back together so that we can find that steady state by working with the eigenvalues and eigenvectors. I don't think we're going to have time for that. So that was like my little pause. But in the future, maybe you'll take a math class and you'll talk about tying that back together. But for now, that was just my fun little interlude. The way we are going to find those steady states, and think about the steady states really similarly to thinking about equilibria, right? When we're looking for those equilibria, we're trying to see what's happening far off into the future. And if we get to a steady state or an equilibrium where things are not changing, what that looks like for these Markov transition matrices is, for example, on that 2x2 matrix, if I started, and I'm going to call them T and G for Ticantine and Guads. So if I started with Ticantine and Guads, if I'm at a steady state, then I've gotten to a place where I've hit that magic distribution where what comes out is the same as what went in. So if I'm looking for the steady state distribution, I'm going to write out these equations. So I've got x, y, z times that first row. So 0.1x 0.3y, 0.5z is equal to x. If I take my row times my second column, I'm just going to get that 0.3x is equal to, and again, because I'm doing my because I'm doing like my second entry now, that's going to equal y. And I'll go ahead and put the zeros in there. And then for my third entry, I've got my row times my column. So that's going to match up to z. And I've got 0.6x plus 0.7y plus 0.5z is equal to z. And then my last equation is going to be the same every time. And that's that all of my probabilities have to sum up to 1. So we have all kinds of options for how to solve this system. But I'm looking at this second equation and it looks pretty friendly to me because I already have y determined by x. So I think I'm really gonna focus on this one and use it to manage my other two. Yeah. So that second equation here, if 0.3x is equal to y, I'm just gonna kind of hold on to that. And I'm gonna almost ignore the x plus y plus z equals 1 for the moment, and I'm gonna focus on the other two equations. So it looks like if I were to, I don't know, or we could put it all in a matrix and row reduce it. Anyone have preferences?
I don't know. I think that is
Okay.
Like 0.
Okay, so I'm going to substitute this into my other equations. Is that what you meant by substitute?
Mm-hmm.
Yeah. So if I take that in my top row here would become 0.1x plus 0.3 times 0.3x plus 0.5z is equal to x. So 0.1x plus 0.3 times 0.3 will be 0.09. So that's 0.19. So I have 0.5z. If that's 0.19, then this must be 0.81x after I subtract it. How'd I do with my arithmetic? So I can write this as z is equal to, if I multiply both sides by 2, that would be 1.62x. And because I have y in terms of x and z in terms of x, I can put all of that back into the x plus y plus z equals 1. And hopefully get an answer. So x plus 0.3x plus 1.62x has to be equal to 1. So that's 1.3 plus 1.62. So 1.92x would be equal to 1, which would give me x is equal to 1 divided by 1.92.
Is it 2.92?
2.92. Yep, 2.92. So close to 1/3. And that would make y equal to 0.3 divided by 2.92. And that would make z equal to 1.62 divided by 2.92. And at least all of those numbers are positive and between 0 and 1. So it's totally plausible.